So there's a quantity that's useful in describing the net effect of a force on an object. So let's imagine we have an object, right? And we have a force acting on that object for some amount of time, right? For something like delta t. It turns out if you plot force versus time, and you could even imagine maybe the force has a beginning, right? At some point, maybe you push on this ball, right? So just as you start to push on it, the force is 0 before you're touching it, right? And then it goes up, and you push on it for a little while, and then you let go. So this distance here is some delta t. So the net effect of that force acting over that time turns out to be related to the area under this curve. All right, so we could say area. So the area under that curve is something that we define as impulse. We use a capital J for that variable. And you notice here that the impulse, the area really is going to be not super easy to calculate, right? Because the force there is really wobbly. So we're not presuming that the force versus time here has any particular shape, right? And you might imagine for different classes of materials, maybe it would have different shapes. But another thing we can do for this, for impulse, is say, well, there must be some average force acting over this time that would give me the same area. So we say, okay, what if we modeled this like a rectangle? There's probably some rectangle with the same area. That's probably not that one. It's probably a little higher. There's probably some rectangle with the same area. We'll say same area. And the height of that rectangle could be a good definition for an average force. So another definition for impulse could be F average times delta t. That turns out to be a pretty useful expression. The average force acting over some time. So let's talk about this for just a second. The impulse on an object is sometimes a fixed thing. So imagine like a toy car running into a wall, right? So you push the toy car along the ground. In fact, we could draw that, right? Here's a toy car. You can tell because it's smaller than the cars I typically drive. With some velocity, right, headed toward a wall. And then afterward, let's say it's just at rest. So it hits the wall and it comes to rest. The average force acting on that car is related to the impulse and related to the time that it's acting on here. So the impulse here is a fixed thing, all right, because the car is coming to rest, and we can adjust the average force by changing the time of this interaction. You know what? Let me do one bit of math on this, and you'll see why. All right. So far we've got two definitions for impulse. We've got J equals the area of F versus T. J is also and F average acting over some delta t. And let's play with that equation for a second. F average delta t. F average would be m times A average, right? So I can say m times A average times delta t. That's just invoking Newton's second law. Shows up everywhere. Remember that average acceleration is by definition delta v over delta t. So I can plug that in for A average, m times delta v over delta t times delta t. Do you see that the delta t's go away? And so I'm left with m times delta v. And usually mass is not a thing that changes, so I could move the delta outside of the mv. That's a step of like pseudo-calculus, basically. So it looks like impulse leads to a change in some quantity, m times v. So we define another variable, p, to be m times v. This is momentum. So p equals m times v. So the impulse here could be written as delta p. Okay, so momentum, that's a useful quantity or useful idea. Momentum captures information about an object that includes both its its velocity and its mass. I mean, that seems obvious. It's actually super useful in collisions. So you imagine catching a sports ball. All right, so what do I mean? Well, imagine catching a baseball, right? How much does a baseball weigh? It's like 140 grams, right? But the effect of that impact, right? The energy you've got to absorb depends on both its mass and its velocity, right? If that's a 90-mile-an-hour fastball, that's gonna hurt, right? You could also talk about, what about a 90-mile-an-hour ping pong ball? Well, it's still going the same speed, right? It's still going 90 miles an hour, but the mass is a lot less. Also, if a ping pong ball were going 90 miles an hour in air, it would slow down very quickly. But if we could ignore air, if air weren't there, then you could ask, which one would you rather catch? I think the answer would be the ping pong ball, particularly if you don't have a glove, right? Okay, so all of that is to say, this is a new quantity, this momentum. And let me erase some of this and say, impulse, the impulse on an object leads to a change in this variable momentum. Right, so I can say this, J also equals delta P. So here we have three definitions for impulse, and often it's useful to use two of them at a time to be able to solve for one thing or another thing. And that brings me back to this example. So when this car hits the wall, the change in momentum for that action is a fixed thing, right? It starts with some P initial. Let's use tealish. There's teal. So there's P, and P final is 0. Now, as long as this car comes to rest, delta P is a fixed thing. But I can adjust the average force and by adjusting the time of the interaction, right? So if this hits a concrete wall, delta T is going to be small, so F average is going to be large. And if this hits a foam mat, delta T would be larger and F average would be smaller. Okay, so let's look at an example. Example number 1 here says a baseball is pitched and reaches the batter at traveling horizontally at 20 meters per second. The ball is hit and leaves the bat traveling in the opposite direction at 40 meters per second. It gives us a time of the interaction and asks for the average force. Okay. So let's draw this. I'm going to draw it as a before and after, kind of like we did for energy problems. So before, I have a baseball coming in. Let's let it start by going to the left. Right, we have a choice in that. So here's my baseball. That doesn't look like a baseball. Sure, perfect. There's V initial. The bat hits it, and V final is exactly the opposite direction, but a little faster. Right? We could write those things down. Let's make it green. So these are the known things. V initial is 20 meters per second, and you know what? It's going to the left, so I'm gonna define. Here's my positive x-axis. So that initial velocity is negative 20 meters per second. You'll see what that matters in a minute. V final is positive 40 meters per second. The time for the interaction is 0.6 milliseconds. And that kind of time scale for these interactions is pretty typical, right? Single to tenths of milliseconds is a pretty typical time for this interaction. The question is, what is average force, right? So find F average. Okay. So we are going to use two sides of the impulse definition. One of them is, I'm going to erase a little bit of this. Just give myself some space. One of them is J equals F average delta T, because I know delta T, and I'm looking for F average. The other side I'm going to use, well, I don't have a graph, so that doesn't make any sense. So I'm going to use delta P, which I could write as P final minus P initial. Okay, so let's do another line here. F average is what I'm looking for. Delta T is something I know. I'll plug it in a second. And this is mv final minus mv initial. And if I plug those things in, F average times delta T, oops, I would really like to actually put the number in. So the number here is 0.6 times 10 to the minus 3 seconds equals, the mass is, I think it's 165, no, 150. So 0.15 kilograms, so that we're in the SI unit, times V final is 40 meters per second minus 0.15 kilograms times minus 20 meters per second. And if you do that math on the right hand side, right, 0.15 times 40 minus negative 0.15 times 20, you get 9.0. What are the units on that? Well, it looks like it's a kilogram meter per second. Which is 1 unit for impulse. Right, so kilogram meters per second is the unit of momentum. It's also a unit of impulse. You could also write this as a Newton second if you see force times time. Okay. So that's not the answer. That's a step toward the answer. Right, that's the impulse. And if I divide that impulse by this time, I get a force. I'm going to write it right here. So the average force is 15,000 newtons. That's the answer to part A here, the first part of this problem. Right, that's a very large force. but it's acting for a fraction of a second. And we'll see that's pretty typical for these kinds of problems. So we're talking about large forces that act for very small amounts of time. Okay, so let's look at the next part of this. If the force acting as a function of time were modeled as a triangle, what would be the maximum force? Okay. So here's the force and the time, and let's just start at 0. So we're going to model this like a triangle. So this is like, this length here is delta t. And this time at the end would be 0.6 milliseconds. Okay, so what's the maximum force? That's what we're asking. What's the height of this triangle? Okay, so what else do I know? Well, I know that the area of this triangle is the impulse. Area equals impulse. And I know what the impulse is, right? We solved that in the previous part. That's this number right here. How do I know that's the impulse? Because that was one side. That's delta p, right? That's p final minus p initial. That is this guy, which is the impulse. Okay. So a couple of these circles go away. So, so I just need area equals impulse. Impulse, again, is 9 kilogram meters per second. So I just need the area, and the area of a triangle is half base times height, right? The base is delta t, the height is f max. So I can say half f max delta t. And if you do this math, what you'll find is that f max is, not fax, f max is 9 times 2 divided by the 0.6 milliseconds. It's twice the average. Okay. Is that always the case? Well, no. In the case that we model the collision like a triangle, yes, it will be always the case. But we didn't have to use a triangle, right? We could have used a trapezoid. We could have said, well, it goes to some max, stays there for a little bit, and then comes back to 0. Generally speaking, it won't be a simple thing. Generally, it would be a something funky looking. And if it were this funky looking thing specifically, it wouldn't be as tall, right? It would have to go a little lower. And in fact, the trapezoid should have been lower too. So why bother to model it like something that we don't really expect it to be exactly? It's a good order of magnitude estimate, right? Let's say you're designing a baseball. You ask, how big a force does this baseball need to be able to withstand without, the stitches coming apart and whatnot? And the answer could be something like this. You could say, well, what kind of impulse does it need to absorb or be able to handle? So you could take the average fastball speed, right? Or even the maximum fastball speed. You could use that as your V initial. And then a typical speed at which the baseball leaves the bat, and use that as your V final. Solve for an impulse, and then model it this way. And then you'd probably use a safety factor. You'd probably say, well, okay, this is what I calculate for my F max. Let's multiply by a factor of 4 or 5, and then just make sure that our baseballs can handle that. By the way, you see here why the sign mattered, right? If I had left this velocity positive, this would have been an actual subtraction problem and not an addition problem, and I would have gotten a smaller impulse than I was expecting. And in fact, you see here that the direction of the impulse is positive, right? Meaning the force must have been to the right, right? Because impulse is the same direction as the average force. And that makes sense, right? If for this motion, the baseball bat had to have applied a force to the right to make this happen. So we will see more examples of the vectorness of impulse and how it relates to momentum in the future.